Welcome everybody, thanks for joining. I'm Drew Turner, the Global Marketing Manager for Danfoss Sector Integration, here to present today as a part of the EnVisioneering Connect conference on enabling technologies for heat recovery and integrated systems design. First of all, thing to point out is that the driving factor driving the opportunity for the growth of heat pumps and heat recovery is integration of renewables into the power grid. And in that, we've seen a significant change over the last few years and projected change in the coming years. I was just reading an article today that was talking about the renewables or the growth of renewables into the power grid and what's driving that. But the summary is that we've seen a significant growth in the percentage of power coming from renewables, and we're projecting that that growth is going to continue over the next several years. And the driver for that, as the article was saying, is that the cost is significantly coming down. As with any technology, as you grow in the volume of that technology, every time you double it, the corresponding cost of that technology comes down by roughly half. And as you see here, it's gotten to the point now where renewables, whether it's wind or solar, are both now the lowest cost source of new generation. The only exception to that is energy efficiency, but all of this ties together because the opportunity for efficient renewable heat pumps and the increase of the energy efficiency and tying those together becomes a very critical factor also in the decarbonization. But the main thing to keep in mind is that both renewables as well as energy efficiency are your lowest cost source of energy today. And as that percentage goes up, this is the other thing, is that the corresponding reduction in CO2 emissions goes up. So the business case, if you will, for decarbonization based on heat recovery and heat pump integration goes up as you go forward because of that increase in the percentage of renewables integrated into the power grid. So the decarbonization potential of a heat pump today is very different than that potential in 2030. And the business case and the corresponding accountability that corporations and businesses are being held to for decarbonization needs to incorporate that, and we can help with that as well. But the problem that comes into play as well, as you integrate more renewables into the power grid, is that the integration of those renewables into the power grid creates a disconnect between supply and demand. So as a higher percentage of your power is coming from the sun or coming from wind, then you're at the mercy of the availability of those resources. So that creates a disconnect between the supply and demand. So no longer do you have demand or supply that's governed by demand, you have supply that's governed by the availability of those resources. So that disconnect has to be addressed, and how you address that disconnect is with storage. It's grid level storage, it's demand side storage, it's building storage. Any form of storage creates addresses that disconnect. And I'm going to talk about again later why that's critical. But the form of that storage comes, it takes many different forms. It includes battery storage, it includes pumped hydro storage, and it includes thermal storage. So that's the other thing that's going to come into play in the future, and what you're seeing in the last 5 years is a significant growth in thermal storage usage, both hot storage and cold storage. And it corresponds to the same driver of renewables integration into the grid and decarbonization and the potential for heat recovery and heat pumps. So that's the main takeaway, is that it's all tied together. So I've talked about the drivers. Now I'm going to talk about the focus from an application standpoint. And I'm going to talk about it in the context of what we're doing at our own Danfoss facilities. So Danfoss has committed to fully decarbonize our operations by 2030. And a part of that is showing what's possible at our Danfoss headquarters in Norborg, Denmark. So one of my colleagues in the sector integration team is responsible for a majority of these projects that are being implemented. But you can see over time that decarbonization of the operations of our Danfoss Norborg headquarters, both the reduction in energy usage and then the integration of heat pumps to accomplish that decarbonization. One of the projects that we're working on to do that is retrofitting our own data center. This data center was just installed 2 years ago, but the data center was installed with a traditional comfort cooling system to cool the data center operations. That's now being retrofitted with a water-to-water heat pump system. And this shows the possibility, because this has become, this application experience has become a guideline for also what we're doing with customers now. So doing the same sort of data center cooling system retrofit to recover the heat to the district energy system. And we've learned lots of, several things as a part of this project. One of those is that, and this is going to be no surprise to anybody, but as you increase the cooling temperature, the corresponding recovered heat efficiency becomes more efficient, or becomes higher. So, for example, if you're cooling a data center at 15 degrees C or about 54 degrees, 55 degrees Fahrenheit, you are going to be operating at a efficiency on a water-to-water heat pump based system or water-cooled chiller based system about 3 to 3.5 COP. That's with that higher heat rejection temperature of the water-to-water heat pump. As that increases, that cooling temperature increases up to 25 degrees C, with everything else staying the same, you increase from roughly a 3 COP to up to a 4 COP. So, and the reason for that is because you're requiring less work of the water-to-water heat pump to reject heat at the higher temperature. As you can see from here, also the efficiency of the heating that comes out on the high side, highlighted in red, goes up. And then another takeaway, the combined cooling and heating efficiency, or what we call the symbiosis efficiency, increases as well. That's the other factor that comes into play. We're not really talking about heat recovery, we're talking about integrated systems design, as it's highlighted on the first. That's the main point, is that integrating in these cooling and heating systems to make full use of both all the time is the main summary of what we're focused on today in the sector integration team. And when you do this, and you play with it, from what you see down below in the chart is an individual compressor. What you see up above is the performance of the actual system that was designed for this heat recovery of the data center. And with that, the efficiency is actually higher, about 18% higher than what the individual compressor says it should be at those operating conditions. That's because we can then play with the system design to optimize it to increase the overall efficiency of the water-to-water heat pump system. And this shows why, or how we do that. So the individual compressors utilized, and in this case, of course, it's the turbocore compressors on a water-to-water heat pump, are applied on a first stage and then a second stage water-to-water heat pump system, as shown here on the left-hand side. Each one of those uses a different compressor optimization because of the corresponding work that it has to do. So the low stage and then the high stage have different compressor optimizations because that allows you to increase the overall efficiency of the water-to-water heat pump system. So in this case, that low stage uses a medium lift optimized compressor design, and the high stage uses a high lift optimized compressor design. And this shows it in the symbiosis efficiency terms. So the main point that we're again trying to make is that when you look at, when you transition to an electrified heating system via water-to-water heat pumps, one of the first realizations you come to is that every chiller is a heat pump and every heat pump's a chiller. It's just whether you're making use of both all the time. And the main point with that is that when you look at both the cooling and the heating, and you take advantage of both the cooling capacity and the heating capacity, and then you divide that by the overall power usage to provide both, then the efficiency, or the symbiosis efficiency that I was talking about earlier, is significantly higher than the individual cooling or heating efficiency. So again, shown here are air-cooled chillers that were originally providing the 20 degrees C to the data center were operating on a design day at about a 5.7 COP. As we integrate in the water-to-water heat pump, if it was only providing that heating, it would be at about a 5.3 COP. But the combined cooling and heating efficiency, or symbiosis, is about 9.5. Related to this, and kind of a spoiler that I'm going to talk about at the end, is that we're focused in general on critical facility cooling systems. And this is the biggest opportunity that we see for integration of water-to-water heat pumps or heat pumps and heat recovery into to facilitate the electrification of heating. With those critical facility systems, one of the reasons that we're focused on them is because they all have backup power systems. So whether it's a data center or a hospital or an industrial process application or other forms of or other types of those critical facilities, a lab, all of them have backup power systems. So going back to the original driver of the growth of renewables into the power grid and that disconnect of supply and demand, addressing that disconnect comes in storage, in the form of storage. But it also comes in the form of backup power on the demand side. So if you're providing backup power at a data center, that's power that the grid doesn't have to provide when those renewable sources aren't available. Those same backup power systems are also transitioning to the point now where they're starting to experiment with the integration of hydrogen production into those power systems. And how this takes form is the electrolysis of water splitting out the hydrogen and oxygen, and then a hydrogen going to a fuel cell to generate the power. Both of those processes, the electrolysis and then the fuel cell, are not extremely efficient. But that inefficiency is, luckily for us, also heat. So that same application, if they're running this backup power system that in the future is based on hydrogen, and then operating the water-to-water heat pump to provide both cooling and heating to the district heating grid, then you can integrate in as well the heat recovery from this electrolysis process and the fuel cell power generation that's now powering the equipment for the data center to recover additional heat to the district heating system. Roughly double that of what's possible from the cooling system for the data center itself. Now, another related opportunity that we've been working on, and this is related in proximity based on its closeness to our Danfoss headquarters there in Norborg. But we're also working on several of these other opportunities, similar opportunities in the rest of Denmark. But it's on biogas facilities. So you also have to decarbonize the natural gas grid, and how you do that is with biogas. And the production process of that biogas creates several different heat recovery opportunities. One of them on cooling the slurry to recover the heat to the district heating system, and then also on the upgrade plant where you're separating out the methane and the CO2. Both of those present heat recovery opportunities that we're showing what's possible also at these other facilities around Denmark. Another related opportunity, you'll hear a lot about dual fuel systems or hybrid systems in the future. Most of what that's speaking to is it's not always possible to fully electrify the heating systems. Industrial processes, for example, it's very tough to electrify all of them because of the high heating temperature demand that they have. A boiler or a furnace that you're replacing, the fossil fuel sources, they didn't care what heat temperature they were producing. It was about the same efficiency at 100 degrees C as it was about 60 degrees C. So the difference is that a water-to-water heat pump cares. So every 1 degree C differential that you go up, or 1 K, that you go up in temperature, the corresponding heat pump efficiency is going to go down by about 2%. So that business case, when you get to that industrial application, goes down a lot. How you address this is by creating hybrid systems. So you incrementally electrify those tougher to electrify systems. And then you also give the district heating utilities, in these examples, or utilities, the option to base load those different sources based on the cost of operation. This is an example of one in a district heating utility that we worked on to recover the heat from the flue gas scrubbing from another heat source. In this case, it was biomass. So they were actually burning wood chips, and that was then going into a boiler. That heat was then going into a boiler to create heat for the district energy grid. And that boiler exhaust was then coming off and going into the air. And so they wanted to add a scrubber system on it to scrub out the contaminants coming from that exhaust, but also then to recover the heat from that exhaust system. And so this sprays water over that exhaust, and then recovers the heat via the water-to-water heat pumps that we applied to the district energy system as well. So supplementing that heat provided by the biomass system. This is another one that we worked on, electrification of a heating system for a consumer goods warehouse. And in this system, what we were doing was trying to integrate in their refrigeration and HVAC system. So how we did that was by taking the medium temperature refrigeration system that they had on that warehouse and tying it into a water-to-water heat pump, and then the low temp refrigeration system that they had and tying it into a comfort cooling water-cooled water chiller system. Another application that we've been working on is systems integration of a large refrigeration and HVAC warehouse. And how we did this is pretty interesting because these systems are another example of a harder system to electrify. Tying in a refrigeration system to the HVAC system is a tough thing to accomplish because of the disconnect between those two systems, or the historic disconnect between those two systems. But how we did this was integrating in the medium temp refrigeration system and tying that into a water-to-water heat pump, and then taking the low temp refrigeration system and tying it into the chilled water system via an adiabatic chiller. That then supplies the heat to the air handling units that replace the rooftop units that were formerly used to cool and heat the rest of the warehouse. So now we're recovering the heat from that medium temperature refrigeration, and then we're also increasing the efficiency of that low temp refrigeration system by rejecting the heat to the comfort cooling chilled water loop. And then at the same time, we're eliminating a significant portion of the HFC refrigerants that they were formerly using and replacing them with HFO, which also increases the decarbonization potential. Another example, and this is back to the industrial, this is again a very hard system to fully electrify because they're using both low pressure and high pressure steam, as you see with 130 and 180 degrees Celsius shown on the top right hand side. But what we do have the opportunity to do is take that system where they were taking that low pressure steam and running an absorption chiller based on it to provide cooling to an industrial process at the facility, replace it with a water-to-water heat pump that supplies the cooling to that industrial process, but then also recovers the heat to partially electrify their steam system. And how we're doing this is by preheating the feed water that goes into the boiler. So every boiler system in general has a feed water system. And that feed water system is going to operate, or that boiler is going to operate more efficiently if you preheat the water that's going into it. So we're recovering the heat from that industrial process to preheat the feed water going into that system. That higher temperature that we're rejecting it at also allows them to take the rest of the heat that we can't utilize and send it through the cooling tower, but the cooling tower doesn't have to operate the fans now. So it decreases the energy usage based on that, no need to operate the cooling tower fans anymore as well. And this is an overall summary. So again, the main points or the main takeaways is the best opportunity that we found based on our work in sector integration over the last couple years to integrate water-to-water heat pumps into systems to tie them together and electrify their heating system. The best opportunities are these critical facility cooling systems. But what drives that is a combination of factors. You have a relatively constant load on those critical facility cooling systems, meaning a relatively constant recovered heat capacity. It's operating at a higher cooling temperature, which means that that water-to-water heat pump that you're utilizing to provide that heat is going to operate extremely efficiently. And you also have a backup power system on each one of those facilities, meaning that it has no risk basically has no risk of availability. All of that means also that it's going to be the lowest cost, in the case of a district heating utility, lowest cost future base load decarbonized heat source for that district utility. And this is showing why that's critical. Why is it really critical to make sure that you implement the most efficient and highest availability water-to-water heat pump system? And this is showing a snapshot of the energy prices that we've seen and the fluctuations of them in Denmark over the last 6 months. And actually, on the left-hand side, or in the chart, it shows the variation in just one day in the energy cost. That's because of that same integration of renewables factor. So Denmark today is about 50% renewables in the power grid. Today in the US, we're at about 20%. As we grow up to the percentage that Denmark is at today, we're going to see these same very high daily price fluctuations of electricity cost because of that same factor of the inavailability, periodic inavailability of the sun and wind to supply the grid. That makes it even more important for the heat recovery heat pump system that you implement to be extremely efficient, because it makes it resilient to that price fluctuation. In other words, if you're operating at a 7 COP, then the energy cost that you can absorb with that is significantly different than, for example, an air-to-water heat pump operating at a 2.5 to 3 COP. So again, this is a summary of the learnings. Critical facility cooling systems and heat recovery from them are the best opportunity. Geothermal and comfort cooling systems, based also on our experience over the last couple of years, are generally what we consider to be the second tier opportunity. This is where most people are focused today, because they understand that the ambient air and water centralized heat recovery heat pump systems tend to be relatively inefficient and are not near as resilient to those price fluctuations. So it's really an optimization. Air-to-water heat pumps are going to grow. They should grow because of the same thing, because you still have to electrify the grid and you only have so much heat recovery possible. But focus should be first on implementing these critical facility cooling system retrofits. When you implement these heat recovery heat pump systems, Danfoss has a very broad portfolio of component solutions for those applications. And what we've learned is designing these systems, which again are very complicated systems because you're retrofitting a cooling system and a heating system. And so how you eliminate the complication with those systems is by having experts involved to design them. And we can come in and design these systems and make sure that you have that optimized hydronic system to go with that optimized efficiency heat recovery heat pump system as well. And this is just showing a few examples of those components that we utilize. Components and optimization software that we utilize to optimize the performance of those systems. Thank you for joining this session of EnVisioneering Connect. I appreciate the opportunity to present, and we'll take your questions now.